helps an engineer how we can handle different types of soils encountered in our engineering practice, especially for the road construction. So the fundamental principles of soil understanding scientifically were put forth by Terzaghi. This soul was selected by nature to emerge a new branch of science in civil engineering, soil mechanics. He has given all the scientific background, how to see the soil. It is not like a lump of some mass. There is science within. What is that science? We have to see. Otherwise, our understanding cannot be complete. It is not only life science, but also professional science is here within the ground, because Mother Earth not only serves as a mother to serve us, but also supports us by all means. That support, while it is offering, as engineers, we have to understand so that we can comfortably transmit the loads to the Mother Earth. Then only Mother will be happy, we will be happy. If there is any excess stress, then distress starts. That distress ultimately comes to the surface of the pavement, and ultimately we suffer. That is how fundamentally this understanding is essential to make our systems promising. So let us just have a recap of what we have all studied in our fundamental BTech course under soil mechanics, so that with this knowledge only we will be very clear of what we are really doing. We all studied the soil mechanics with this three-phase diagram in the very second chapter of the introduction. Soil having three phases: solids, water and air. And of course, as long as it is partially saturated, most of the soils are good for engineering works. But the moment the soil becomes saturated, that means no air phase, then problem starts. Those problems we have captured in terms of this effective stress principle enunciated by Karl Terzaghi. This is the very scientific principle or the soul behind all this body. The soul speaks in terms of mathematics. Effective stress is equal to total stress minus pore water pressure. That means total stress we apply from civil engineering loads. That is in our control. But then within the earth, how much really will be borne by the solid particles and how much really be transmitted to the water makes all the sense. Until the load we apply here becomes the load on the soil particles, then it will be in trouble. That is only pore water pressure. Until the load we have applied here becomes this load on the soil grains, that load will be within the water phase, hanging load. That cannot support, actually, water cannot support loads. The moment it is stressed, it tries to go away, but however, when the plasticity is present in the soil and low permeability is the character of the soil we are using, then this water cannot escape. In that way, it creates a lot of problem to our pavements, because a boil will be formed within distress. That distress only ultimately surfaces. That is why only during monsoons most of our pavements will fail. To overcome this very fundamental defect from the soil, this presentation is helpful. Okay, to that extent only our presentation will be made. You see, because of the lack of good soils available across the country at several stretches for the construction of these roads, we are forced to use local soils with some compromise on the specifications. Whatever the fair color soils are present, mostly we use for our road construction, thinking that they are gravel soils. But they are not really gravel. Ultimately, the roads reach this type of muddy state. So some of the failures were reported by late Bhavan Rao, who is a superintending engineer in the department. He has presented in Krishna, Guntur districts how the pavements were failed when engineers used helplessly the local soils for the road construction, because good soils are not available. Anywhere, see, I read on red earth, any fair color soil considered to be good. Color is not at all any index for any character. We have to be very clear, especially as a civil engineer. Even when soft aggregate is used, you see the furrows formed, curves, curvilinearity has become actually. See, furrows are formed along the length. That means they cannot sustain the stress. So compromisation in the road construction does not work because our loads are transient and high intensity tire pressures. And that is why an engineer who is dealing with foundation engineering and roads, he will always confuse. In foundation engineering, even when our soil is little weak, the load applied is static, and whatever the excess pore water pressure that is developed in case there is a development, gradually it will escape under that sustained loading as per Terzagh's consolidation theory. Here, what is that theory? The moment one tire pressure goes transiently within a second, the pore water pressure will be generated, and by the time the soil takes a decision to relieve or hold, it doesn't know, it confuses because time given is very small. The very definition of consolidation is sustained load application and gradual dissipation of pore water pressure. Both should be there. The load applied should stand, and this pore water pressure also goes very gradually. You cannot accelerate it. That is the very definition given. Against that only our pavements work, for which only as an engineer we have to understand. Okay, so let us see in future slides what we can do against this type of weakness. So these are all some of the examples how he has presented the failures and helpless use of these red soils for the road construction, even in national highways, not to speak of rural roads. Some say highly plastic soil is being used in the construction of the road. These are all mudways, actually they are not roadways. This is what we could see by this scenario. Okay, these are all some of the failures he has presented across the coastal Andhra Pradesh. Ultimately, this is how the pavement surface will be subjected to the severe cracking, because the underneath, once the pore water pressure develops, then the system will become very weak, and ultimately under the high tire pressures, this becomes a boil and breaks the whole system, right? That is the problem here. Then of course there are all some of the further problems. See, many roads he has presented in one of the IRC publications in 2005. Anybody can refer. Still so many failures and explanations were given by that engineer. And of course crushed rock base subsequently is promoted as an alternative to this problematic local soils. But however, crushed rock bases cannot be used for all the roads because it is all very costly, and we have to crush our natural hills and hillocks indiscriminately. Ultimately, it is not very good to damage our own national resources. At a later date, we may not see any hillocks in the localities. In fact, these geographical features are essential for the uniform distribution of rainfall. But helplessly, we are all cutting the hills and hillocks around our cities, villages, everywhere because of our construction activity. So this also is not very good. Helplessly, if at all is essential, only we have to do. But even for a rural road, if we employ such techniques, though road is promising, our environment cannot be promising. That is how we have to think. Instead, that is what I am telling, our natural soils are good, but there is a small problem. Give a tablet to that, correct it, use it. Why to crush our own natural resources? This is how we have to think. The whole problem lies in these clay particles present in the soil. Of course, we should not curse this clay particle only our life, truly speaking. Okay, little later we will see under clay mineralogy how this clay particle really controls the whole behavior of the soil. Clays, being negatively charged, holds the water molecules like this. When water molecules are surrounding the clay particle, another clay particle also present here with the same water molecules. Ultimately, this clay particle and that clay particle cannot communicate each other. In between, these water molecules are working like a barrier. Water doesn't have any shear strength except the viscosity. So when there is loading or anything, then it will simply slide. That is what we are calling as plasticity in the soil. This plasticity only we have to overcome. In case as a road engineer, we have to be successful. How to overcome, we will see. See, Bhavan Rao, he has presented some of the research works carried out in the department laboratories by mixing sand content to the locally available quarry soils. Here, these are all the natural quarry soils available in Guntur, Krishna district, Prakasham, etc. You see, none of the soils are satisfying the standard guidelines given for the road construction. What are those standard guidelines? The percent fine should not be more than 10%. Liquid limit should be less than 25%. Plasticity index should be less than 6%. These are all some of the guidelines given. But see, none of the soils are satisfying those guidelines. So, in order to amend these soils, he has tried to mix the sand. You see here also, even when 25 to 30% sand is mixed, the finer fraction is not changed. Only a little liquid limit is changed. That too, here we have to be very clear. Liquid limit test we will do on minus 425 micron size. That means the sand being added must pass through 425 micron sieve. Otherwise also it doesn't have any influence on the plasticity properties. Okay, so normally these natural soils also will contain sand particles. Some 60-70% at least they will have, as per the table also. You see, the percent finer fraction is about 30-34, means the remaining is mostly sand, gravel. Then even for that, if we add the similar size of sand grains of that sand size, then the original finer fraction present still cannot be diluted and it cannot decrease the plasticity. That much understanding we should have, not blindly adding the some sand, the soil will be amended. It is not possible. So that is how here, when he has presented, even with up to 30%, still problem is persisting. So ultimately, the literature on stabilization, we all read in our books or even our manuals like this. General soils based on the particle size will be gravel, sand, silt and clay. And all these fractions have their own distinctions in their behavior. Gravel by itself is good. Sand also good by itself. It does not have any plasticity. So its problem is binding. Somebody should hold it. That is the only requirement when we are dealing with sand and gravel. Here, silt and clay. Silt and clay, because of their small particle size, you see, microns. We are speaking microns, 2 microns, 75, less than 75 microns. Because of their small particle size, their surface area will be very high. And especially though silt by itself is a silent particle, clay is not a silent particle. It is a very active particle. Even when 10% clay fraction of Montmorillonite nature is present, it can control all other fractions. You see, the subtler and subtler the force, the more powerful it is. This is what philosophy. Subtle forces are powerful. And that means it is not these big particles really controls here. This micro particle is able to control the whole big philos. That is why we have to silence this part. Otherwise, we cannot succeed in our engineering. Right? And of course, according when it is not there, you need not silence it, you see. So if your material is predominantly this side, then you can simply adopt some bitumen stabilization or cement stabilization, something like that, so that just to hold these particles, they are good by themselves. There is the end of the problem. But on this side, the problem is not only amendment but also mixing. Mixing the stabilizers with the fine-grained soils is not easy. Little later we will see how difficult it is. So here, that is why our approach should be scientific. How best we can handle both the problems, mixing as well as the effectiveness. To that extent, the developments are like this. Mostly for fine-grained soils, lime stabilization is suggested. And in case the lime stabilization is inadequate to give the required properties, cement stabilization also will be supplemented along with the lime stabilization. We will see little later, this is two-stage stabilization when it will be done. See how across the world this soil stabilization is working. It is all some deep mixing using the lime to form this type of vertical wall, you see. Otherwise we will normally construct a concrete or masonry retaining wall. Instead, it is all only deep mixed soil column only, soil plus lime or soil plus cement. They will mix like this. Then after setting, it is becoming like a wall, right? So this is the technology working. That means the stabilized soil is able to stand like this. Why don't we use these type of ideas? You see, even vertical cuts with this much load, after the installation of the stabilized soil columns, they are standing. That means stabilized soil is very good by itself. Similar advancements we can make in our road engineering also to make our roads promising with simple amendment. And in this direction, the different approaches, see, normally mechanical stabilization, then admixture stabilization will be predominantly used. Mechanical stabilization means, see, a particular soil may not be able to satisfy the required gradation and plasticity. Okay, then try to mix some other better soil so that we can amend this soil. By mixing 2 or 3 locally available soils, if we can get the specifications close to the specifications, that is also good. Now let us see what the code suggested. Soil plus some aggregate mixes were suggested like this for the sub-base and base courses. These are some of the gradations suggested, but here you see the guideline. Minus 425 micron size should be just 15% around average. And this is again stringent. 75% fines should be very less, 4 to 8, and here at the most. That is why I make a general statement less than 10 here or here, something like that. So finding this type of very good soils having percent fines less than 10% is very difficult at several project sites. It must be a desert-like soil. Okay, Mother India is not a desert. That is why only we are fortunate to get our food and juice. So to that extent only we have to amend these soils so that we can address this one problem. Until we address this last line, our success cannot be there, because that will control all other gradation. Okay, so that is why here you see below this table, liquid limit not to exceed 25%. Here also liquid limit not to exceed 25 and plastic index not to exceed 6%. That means these guidelines are very stringent. Very rarely we will satisfy these two guidelines. Most of the Indian soils, even if they are good, okay, Telangana Moram type soils, some pockets, the liquid limit will not be there. They are non-plastic. But otherwise, even Moram soils also predominantly will have the liquid limit between 30 to 40. And I have seen Moram soils having liquid limit even 62%. We'll see little later what we have done with that type of soils. Yeah, and these are the requirements for the surface layer. The liquid limit is allowed up to 35%, because at the top it should be little smooth. And of course here the percent fines are limited to only around 15%. So these are very difficult to be satisfied. That is the whole problem. Writing the guidelines is okay, But in reality, we may not realize this type of stringent guidelines with natural soils. And other amendments suggested sand clay mixes for different types of soils. See, if at all only clay is there, add some sand. If only sand or gravel is present, add some other clay type soil, so that we can use them in the road construction. This is what this amendment, sand clay mixes. Then here, clayey soil for sands and gravels. That means sands and gravels are available, but only sand and gravel cannot be used because there is no binding. They can simply erode under the flow, and the confinement is required. No? That is why somebody has to hold these particles. Then some clay content is to be added. That is suggested to be around 10 to 35%. Sand for silty soil, only silts are not at all suggested for any engineering use. This is the general truth. We study in soil mechanics. Silty soils cannot be directly used for any engineering works because they are prone to be eroded easily, scoured. Then some sand must be added, means that sand 15 to 30% is suggested for the silty soils to amend themselves mechanically. Only black cotton soil is present, for example, then to amend it, 40 to 60% sand is suggested to be added. But you see, where is sand now? Can we really use these ideas? Very difficult. Sand has become gold now. So because of this type of ideas, though they are all given in our codes and manuals, in practice we cannot follow these guidelines. And moreover, see the stringent guideline here, liquid limit should be less than 25, plastic index should be less than 6, minimum C bar 20%. Even if we do all this, there is no guarantee that we will get this specification satisfied. For example, here you see 40 to 60% of the sand you might have added, say. But then the whole problem is the remaining 40% is clay. That clay, 40% clay is very high to control the remaining 60%. It will only be again become mud if at all that soil is saturated. That 40% black cotton soil will control all these properties. You can never satisfy this guideline by using only sand mixed with the black cotton soil. This is a great truth in reality. That is how only, though these guidelines are given in our manuals, in practice difficult to satisfy the specifications. Then normally in Telangana, Moram soils are predominantly available. Just now, as I was telling, Moram soils by themselves are good, 80% sand, gravel, etc. But however, that remaining 20% around is again fine grain fraction, silt plus clay. Liquid limit will be always about more than 30%. Then that is enough to damage the properties of Moram soils. That is why most of the Moram soils, though they are generally considered to be good, the CBR value will be less than 5 only. Right? So then people think sand we can mix with that Moram soil to amend it. As I said, sand available itself is a big problem. And what type of sand we are getting? Because I told within this itself 80% sand is there already. Adding some same size of sand is of no use. Minus 425 micron size passed sand, whether it is available or not, we do not know. So with this much constraints, satisfying the material specifications using mechanical stabilization alone is in practice really difficult. And here some more suggestion. Okay, your soil is not very good, then add about 30% aggregate to that soil. But again, this guideline you see, plasticity index should be 8 to 11% and sand must be greater than 33% within this soil. This again a very stringent guideline, not easy to satisfy. See, ultimately this soil property only will control. Please understand, adding this aggregate does not change this original plasticity property. Originally this soil should have this little plasticity index, means that soil must be good by itself. Such good soil is not available, not to speak of our trial with this aggregate. This is the very root problem. one has to understand, especially with respect to our Indian soil conditions. Then lime stabilization, this is again admixture stabilization. That is what we have seen under the table. Mechanical stabilization means amendment of the gradation and plasticity by admixing different types of materials, aggregates, soils, etc., so that we may get the required gradation and plasticity amendment. But however, as I have already said, not very easy to satisfy these specifications in reality. Now, this is stabilization, that means admixture modification, whether lime, cement, all these materials comes under admixture stabilization. So, lime stabilization is normally suitable for clay soils. One has to be very clear at this point, lime by itself is not a complete binding material. Only hydraulic lime is a complete binding material. We have studied in our building materials different types of limes. Hydraulic lime consists of about 30% clay. That is why it is having the cementitious properties. That is why it is called natural cement. All other limes, they cannot act like binding materials except little carbonation. For such limes, if at all we have to be forcibly use such limes which does not have any of the cementation by themselves, then we have to induce the cementation by additional support. That additional support comes here like this. For example, quicklime you have added to the soil by itself is not a binding material. But however, quicklime changes the pH value of the soil. Once the pH value becomes more than 12, then the clay particles will respond to that alkaline environment. Alkaline environment is aggressive for the clay particles. Under that high alkalinity, the clay particles gradually lose the very silica and alumina from the central mineral structure. The moment silica and alumina comes out of the mineral, the calcium Ca is already waiting for those ions. Then calcium silicate and calcium aluminosilicates will be formed. That is how cementation will be induced. But this process to happen, it is a time-taking process, slow. It is very gradual. Pozzolanic reactions are very slow. So that is another problem with the lime. So that means what we have to understand, lime, most of the limes by themselves are not binding with the soil, and they have to depend on the help from the soil. That help comes gradually only in case the soil is responsive. There is no guarantee also for all the soils to respond. So initially we have to understand whether the soil responds or not. How to then check? See here, the check is given. Add different limes of different percentages of lime, then check whether 3 kg per centimeter square of unconfined compressive strength, if it is giving at 7 days curing period, then there is reactivity between the lime and the soil. This indicates, okay, then we can go ahead. After that, these general guidelines you see for these materials to be followed. In the lime, calcium oxide should be greater than 70%, and in the soil we are taking, you see, minus 425 micron size, 15 and minus 75, 10% must be there, because just now I was referring, these clay mineral particles have to help this lime, otherwise cementation may not be there. Only hydraulic lime can do that, but most of such pure hydraulic limes, they do not be added to the soil, they will be used for other purposes. That is again we have to be very clear. And sulfates, if at all in our soil they are present in higher content, then also we should not go for lime stabilization, because lime plus sulfates produces another unwanted mineral called yttringite, which by itself is again another swelling mineral. That yttringite unnecessarily damages the pavement system when it swells like black cotton soil. Okay, so that is why when we are going for lime or cement stabilization, these are all some of the checks. there are some certain failures also when this type of sensitive points are not followed, right? And another difficulty you see, just in the very beginning I said mixing and the cementation. Mixing, for that the manual suggests the local soil must be pulverized to this degree of fineness, minus 4.75 mm up to 80%. 80% soil must pass through this size, and 100 all the soil must pass through 75 mm. So you see how difficult it is, especially with clay, to reduce the particle size just to peanuts. Not easy. These are all some of the difficult things, especially in Indian conditions, because we do not have the correct equipment, those machinery for stabilization. Then amount of lime for different soils is suggested like this. You see, alluvial soil, moram type soils requires about 3% lime for their modification. This plasticity must be there. Otherwise also lime does not work. Of course, if it is non-plastic, we need not stabilize also. We have to go for other method of cementation in case it is required. Otherwise, by itself, if they are good, they are good. Morams, etc., by themselves, they are good. However, if plasticity is present more than the requirement, then we have to amend it. That is why only the suggestion is made. Clay or BC soils, 3 to 5% lime is generally sufficient. Highly expansive clay, then 5 to 6% is suggested. Again, you see, these are mostly to address the plasticity problems. But then the other requirement, CBR, sometimes 20 to 30% CBR value we should get after the amendment. This is another problem. Most of the time we may not get this, for which a little higher lime content is required. Because initially some 3 to 4% lime will be consumed by the soils to address their own plasticity. Only when the plasticity is overcome, then only strength will come. You see, this is CBR means it is a strength index. Strength comes only when plasticity is overcome. That much clarity we should have. Both do not go side by side. If more plasticity is there and if you say there is a lot of strength, nobody will believe. So these are some of the critical points we have to think, not simply to address the plasticity problem, but whether we are getting the CBR or not also must be checked. Then for the base course, if the stabilized soil itself is being used, then 80 to 100% CBR we should get. So these are some of the critical points for the lime stabilization. It may not happen because of the lack of pozzolanic reactivity. In that case, that is why only all these checks are to be made. Then initially you use lime to address the plasticity, then supplement the cement rather than depending only on the lime to get these additional CBR values. Then of course, between the field and laboratory, always there is a difference, because in the laboratory we handle very few kgs of soil where mixing everything can be controlled, but in the field it is not like that, for which the code suggests only 2/3 the value obtained in the laboratory is to be considered for the field. Okay, right, then these are some of the precautions as an engineer we can do. Combinations, for example, you see some soils do not react with the lime, but still you want to use only lime stabilization, not cement. In that case, yes, there is a possibility if you can use fly ash like material, fly ash, GZBS, etc., if they are available close to the site, then along with the lime, if we add such pozzolanic materials, then also we can go for lime stabilization without doubt. Soil may not react, but however, this pozzolana and lime will react and ultimately bind the soil particles. There also we will satisfy our requirement. And of course, if fly ash alone is available at the site, the code again suggests fly ash and lime itself can be used. Okay, it becomes hard actually. Fly ash by lime stabilization, if it is reactive, becomes hard. Then that can be used for the subbase and base courses, avoiding soil altogether. Then of course to do this, the guideline you see here, we have to check blindly, we should not go for anything. 15 kg per centimeter square or 1.5 MPa unconfined compressive strength we should get at 28 days curing period between the lime and fly ash. Only then we can go for this type of application. Then for the fly ashes, we all studied class F, class C. Class F means siliceous fly ash, where the silica content is more than 70%. By itself, the lime content is less. Otherwise, it will have some pozzolanic reactivity. That is the meaning of siliceous fly ash. Calcareous fly ash by itself contains sufficient lime contents, calcium oxide, generally more than 10%, and the silica content must be 50%. This is how these fly ashes are categorized under Indian conditions. Class F and Class C means only this. The siliceous fly ash is represented by F, calcium oxide less than 10%, calcareous fly ash represented as C, calcium oxide greater than 10%. And it is not enough to see the total silica content, but how much of it is really tasteful is important. That taste comes only when it is reactive. Okay, silent silica is of little use for the stabilization, because I have already told lime by itself is not a full-fledged binding material, depends on other materials for their contribution to get the binding. That contribution comes from the other materials. Means, for example, here we are depending on fly ash. In that, the reactive silica must be present, not the total silica. 20% must be there if at all we depend on fly ash for inducement of the cementation in the soil. Then these are some of the reactions possible between the soil and lime. Immediately when quicklime type lime is added to the soil, hydration, flocculation, cementation, carbonation, these are all some of the short-term reactions. Hydration means the quicklime gets the water from the soil and makes the soil little dry instantly, and that is how it becomes workable. Flocculation, this flocculation happens because of, see, it is like our sedimentation of drinking water using alum. Here also the similar condition will be prevailing. Once the lime is added, calcium ions are present. These calcium ions sit on the clay particle surfaces so that the negative charge will be satisfied. Once the negative charge is satisfied, the clay particle become little convenient and happy, and when it is happy, it can do friendship with the surrounding clay particles, and when more clay particles are under friendship, they will make the flocks. When such flocks are formed, the surface area will be reduced and water affinity will be reduced. The material becomes workable. Okay, little later under clay mineralogy also we will see the similar concepts. Of course, these are all very quick reactions. Within 1-2 days it will happen. Cementation, of course, it is not that immediate. It takes time. Generally, the code says if everything is maintained, that means sufficient moisture content, temperature, everything, up to 28 days curing period is required to get the cementation. This is the long-term reaction. These are the short-term reactions. Carbonation is only attraction of carbon dioxide from the environment so that the calcium oxide becomes calcium carbonate. A little strength gain will be there, but that much small strength gain in civil engineering we will neglect for our professional purpose. So the cementation, if it comes by pozzolanic reactions, that is only our real contribution. Otherwise, forget about the strength. This immediate benefit of plasticity modification by these reactions is okay. Then we will go for cement stabilization in case more strength is required besides the plasticity requirement. Then the benefits: reduces the plasticity, just now I was referring, improves the workability. Once plasticity is decreased, workability will be automatically improved. Strength improvement will be there when cementation is there. Then of course permeability, soil becomes little permeable because the flocculation reactions takes place when the particle size increases. Because of the flocculation, the void size will be increased, and when void size is increased, the permeability will be increased. There are some clays where 1000 times increase in permeability is possible after lime stabilization. Then of course if it is swelling type soil, that properties also will be modified by the lime stabilization. That is why for black cotton soils we suggest the lime stabilization. These are all some of the changes that happen when lime is added. Liquid limit is decreased a little and plastic limit will be increased. The net effect will be reduction in the plasticity index. Once this plastic index is decreased, then soil will become little friable, workable, easy to work. Otherwise it will stick to the rollers, everything. Nobody can work actually with this type of clays. That is why at least lime facilitates the material not to give such working troubles in the field. And another important point to be remembered, when lime stabilization is done, the density will be slightly decreased because lime by itself has the specific gravity less than soil, and it is very fine powder we are adding. That is why the density will be slightly decreased. However, we have to remember that slight reduction in density, the subsequent strength loss will be restored by cementation reactions. So it is not a really loss. A little compromise in the density, but however ultimately we will get more strength only because of these reactions. And one more precaution: in case of cement stabilization, with increasing cement content, the strength keep on increasing. But however, in case of lime, this much clarity must be there. Up to certain extent only it will increase, and beyond that it will fall down. So that is why we should not add lime in excess than the requirement. In that case, lime will remain as free lime. That means free lime particles. Free lime by itself has strength. We have to be very clear. In direct shear test, if you fill lime powder and another direct shear mold, some soil sample, if you shear, the shear strength of this lime and that soil will be very much different. Lime has a low shear strength by itself, that powder. So in case the soil containing only free lime powder having no reactions, then the matrix will be damaged, is it not? The strength will be reduced. That is why lime to lime, that means easily slides one over the other, then strength reduction is present. So it is suggested to use lime judiciously only within the requirement, not in excess. Otherwise unnecessarily the strength will be decreased. Yeah, here the fundamental understanding with respect to this clay particle can be understood. All the clay particles in this world are made up of the clay minerals, and all the clay minerals are again made up of only these two fundamental building blocks or basic units: silica tetrahedron, alumina octahedron. These are only the two basic structural units which make all the different types of clay minerals like kaolinite, illite, montmorillite, chlorite, any vermiculite, anything you name, all of them ultimately will be made up of only these two basic structural units. The silica is represented like this, and trapezium like, whereas this is called alumina octahedron. This is represented as the rectangle to show the stocking. For example, you see montmorillite, we will say highly swelling, expansive clay, something like that. That is, see how it is made up of this sheet central on both the sides, two silica sheets, and again another montmorillite mineral particle. Then in between you see the bonding is not there, only water and ions are present. This will not be permanent, always keep changing whenever there is a change in the surrounding environment. That is why these soils are not stable, because of the lack of the permanent bond between these two particles. Then why at all they are not silent? Now let us understand where from the activity is coming in these clay particles. You see, I said these are the basic fundamental units that are forming all the clay mineral particles. By itself, silica tetrahedron means centrally silica, and these are all the oxygens. Here, alumina, and these are all hydroxyls. By themselves were born happy, everything is satisfied. By silica plus 4, then 4 means 8. Again, that 4 will be satisfied. This bonding will be continuing. It will share another 4 with other surrounding continuity chain. So everything is balanced. So happy. Here also the same thing. This bonding also continues, and then this plus 3 will satisfy. Everybody is happy. Only balance gives happiness, neither excess nor the deficient charge will ever give any happiness. This is what we have to understand even in our life also. So here, but however, friends, it is not that everybody will be happy in this world. This world is not for that. That this is only the central philosophy of all our Vedic literature. This is only our launching pad. It is not a permanent homeland for our life. Ultimately, we should be liberated, something like that. You see, that is what we read. All that also we can understand through this clay particle philosophy. Here, this happiness cannot sustain for long time. Around it, the environment is prevailing. In the environment, all cations will be present in the Mother Earth. Sodium, potassium, aluminum, not zinc, magnesium, everything. This silica will be targeted by alumina from the environment. And this fighting goes, and suddenly one aluminum ion will succeed to enter into this heart, and ultimately this very heart will be transplanted here. That means originally plus 4 is replaced by plus 3 now. That means one negative charge deficiency is already created silently. Though the structure by itself is not changed intact, the very heart is changed. Accordingly, charge is created. That charge, how to satisfy? Here also the similar problem will arise. Plus 3 aluminium will be targeted by the lower valency cations like magnesium, and one of the magnesium ion will succeed to enter in the place of this aluminium, then again creating one deficiency of negative charge. Like that, if every mineral is subjected to such changes, the negative charge will be predominant. That means originally everything is balanced, now become negative. Okay, so that is why only we all be suggested by some of our mentors, be positive, but that be positive is not really possible always, because this induced negative charge is already there within all of us from the very source of our creation. We are all coming from the Mother Earth. This clay is only our support. All our food and juice will come from this clay fraction only, not other fractions. We have to be clear. Silt, sand, gravel by themselves, they cannot support any life. That is why one of the agriculture scientists says clays are full of life with excellent microbiological systems responsible for the sustenance of life for the past millions of years. Even Swami Vivekananda, in his own philosophical statement, clay, if you understand clearly a lump of clay, you will automatically understand the whole mass of clay in the entire universe. That means clay was very much praised by these great people. They realized the importance of this clay particle, maybe through their wisdom. At that time, there was no clay chemistry or something like that, but still they could realize the importance of this clay particle. So then friends, once the negative charge is present, then these clay particles become unstable. Then they cannot die, you see. Again, the environment helps this negatively charged particles to satisfy their own charge deficiency with the help of the surrounding cations present in the environment. But you please understand, environment will never be under any control and it cannot be stable. Always it fluctuates. Okay, in our life also same thing, you see, here also the same thing. This environment between the clay particles will always changing. Then whenever there is a change, the deficiency will be changing and it has to struggle to catch hold of the cations of whatever the cation available, and sometimes good cations may be available, sometimes good and bad here arises only the valency friends. In case sodium ions are only present, say for example, sodium valency is only 1, to satisfy 100 charges, 100 sodium cations are to be held by this clay particle helplessly. Then nuisance, you see, the more you attract, more nuisance will be there. This is what in our life or in this clay. That is why ultimately I understood our life is not very much different from this clay life. So here more ions will come, means more nuisance will be there. That is why only sodium monomerlite is more problematic than the other monomerlite like calcium or something. For example, calcium is present for 100 deficiency, 50 calcium ions can do the purpose. That is how they are happy. Okay, then if for example aluminum is still present in the environment, only 33 or 34 can do the job. That means happy. Less number, more happy. Same thing is true here. That is why only lime stabilization we are adding now, because okay, lime being divalent cation, it can pacify the negative charge significantly so that the material will remain silent, and so that we can design our structures little happy. This is the entire philosophy of our lime stabilization or cement stable anything. Ultimately, our success lies in silencing these central clay minerals. Then we have taken up little work at NIT Warangal to understand how, see, ultimately reading alone is not sufficient. As a professional, we have to have some hand-on experience. Otherwise, you will never become confident of any idea or engineering. That is why only we have taken up some little research work at NIT through our MTech project works. See, here we have taken a fly ash to experiment. This is the fly ash collected from thermal power plant and it is classified under class F. Just now I was referring, it is, that means siliceous, lime content is less. This is how the scanning electron microscope shows the fly ash. They are all hollow spheres. They are also called spheres, hollow spheres. Chemical components, again GGBS, ground granulated blast furnace slag, also we used for our study. Actually this GGBS is very promising compared to fly ash based on our observation, because here the calcium content you see more than 30% and silica is sufficiently there. That is why sometimes GGBS by itself is becoming very hard, even little content. So to the soil, when we have added the UCC value, see how it is increasing to the fly ash, and lime when we are using as the stabilizer, the UCC value is steeply increased with increasing lime content. Then fly ash, lime, GGBS, along with fly ash, GGBS also used, so that when in the presence of lime, these become binding materials. Like this, you see when GGBS is added, the strength increase up to 100 and more than 100 kg per centimeter square, unconfined compressive strength. With only fly ash, it is only about 30. So the GGBS found to be very effective in giving the strength. Cement, of course, works well with any material because by itself is a complete binding material. Then these are some of the ideas what we got. For example, see, the IS code gave the different compressive strength values for the bricks, first class, second class, third class, fourth class bricks. For this, what are all the mixes satisfying the requirement? Based on our research, we understood these are all the mixes possible to get these strengths. That means brick making is possible if these mixes can be followed. And water absorption also satisfied. That is why these are all successful combinations we have written, because water absorption limits are also given for every category of the brick, and these mixes have satisfied those requirements also. And for our road engineering, see the IRC suggests 45 to 70 kg per centimeter square between 7 days to 28 days curing period. For that also, our experimental results for different combinations at different curing periods, we got the confined compressive strength within this range, and the percent weight loss, etc., were again satisfied. That is why successful combinations only I have presented here. Interestingly, you see, fly ash and GGBS alone also is able to give the strength, sufficient strength. Okay, cement even not added, lime not added also is becoming strong, because GGBS by itself is having lime content sufficiently. Even 25% cement is not able to do the job what this fly ash and GGBS could do. You see, this is a beautiful observation. See, normally in civil engineering, we should not believe any of this type of results unless ultimately the material is tested like this. When they are dry, everything is good. When they are fully saturated, then only in civil engineering all the problem starts. That is why our testing should end with the saturation condition only. That is why CBR soaked condition we will test. Here also, at the end of the test, just I have put most of the samples in water to check whether there is any possibility for disintegration or not. Okay, they're all standing means by themselves are okay now. That means the results we can believe. Then cement stabilization, types of soil. See, in cement stabilization, as I have already said, cement by itself is full binding material, complete. So here cement again must be judiciously used. We should not go blindly. See, long back during 1930s itself in Britain, they have used this cement stabilization for the road constructions. Then the Britishers have categorized the soil cement mixes like this very scientifically. Do you want more strength? Okay, then go for this 5 to 14% cement content. Use that mix for base and sub-base cores. In case you are using for some erosion control work, slope protection, okay, use the same cement content, but add more water to get the mortar consistency. That is what I suggested. Here, this line is very suitable for road engineer. Modified soil cement. Here, the suggestion is the cement content is only less than 5%. Generally, this can be used for subgrade. Original subgrade itself is not good. Now, the stringent guidelines are CBR must be greater than 5, and for higher roads greater than 8. All those guidelines have come. But many subgrade soils are not satisfying that guideline. In that case, less than 5% cement we can use to modify this subgrade soil itself to get the minimum CBR required. Okay then, so CBR can be greater than 25%, making the material suitable for sub-base or base courses. That is how we also study it. A little later we will see. It is really very promising, especially with Telangana Moram soils. 3% cement is generally sufficient to overcome most of the specified guidelines. No lime, no sand, no other amendments are required. That is the beauty with this one idea. Then of course the guidelines again from our own manual, it is given how the gradation of the material for this soil cement stabilization to be used. More favorable gradation is given here. And here also the same problem. The degree of pulverization 80% will be less than about 5.6 mm, and all the soil must pass through 26.5 mm. That means pulverization is not that easy, especially with the clay soils to this degree. Little later, we also face the same problem. I will just show some figure. Again, suitability. Just now I was telling, cement being little costly material, one should not attempt for all soils. It is precious material, you see. It is used in concrete and other higher end products, but we are using with soil because of our difficulty. So then we must be little cautious where to use, where not to use. For that, the guidelines are given. You see here, a useful rule for soil selection for the cement stabilization is plasticity modulus. Plasticity modulus is the product of plasticity index and fraction passing through 425 micron sieve. It should be less than 250, and uniformity coefficient Cu in our sieve analysis will come across D60 by D10. That should be greater than 5. This is how the guideline is given. For such soil, cement stabilization can be favorably used. And of course, sulfate content should not be more than this. As for the lime content, lime stabilization, here also the same problem will be there, because during the hydration of the cement, again free lime will be liberated. And in case the sulfates are present, ettringite will be formed. Once ettringite is formed, the swelling starts. Another problem. Unnecessarily we induce the swelling. It may not be originally black cotton soil, but the similar problem we unnecessarily induce in the presence of sulfates. These are some of the other guidelines. You see, liquid limit should be less than 45, plasticity index should be less than 20 for cement stabilization to be used. Then the required unconfined compressive strength with cement stabilization for different purposes is also given. Old code suggested 1700 kPa, that means 17 kg per centimeter square at 7 days curing period, but the revised code now increased this value to 28 kg per centimeter square or 2800 kPa at 7 days curing period. Then of course for subbase the minimum suggested value is like this. That means to get this directly we do not know. Some experiments we have to make using different cement contents, and that cement content satisfies the required values is to be selected. Then of course these are all like the factors affecting cement stabilization: quality and amount of water, mixing, compaction, curing. This is all known, friends. More water should not be, water cement ratio, everything, quality of water, what all we studied in our concrete technology, also true here. Because here also the same cement is acting. That means here organic matter, etc., if it is present in the water, that damages the cementing property of the cement. So again, water cement ratio law, Abraham's law, is still true even with the soil stabilization, not only in concrete technology. Same points are here mentioned. And here also mixing, compaction, curing means mixing should not continue beyond the initial curing setting time, and compaction should be close to the OMC and slightly higher than OMC. All these are some of the guidelines given, and at least 2 weeks curing must be maintained to maintain the moisture content. Again, admixtures, this is again important aspect we have to remember. Just in the very beginning I said, in case you are going for say black cotton soil and you have selected cement stabilization, keeping in view the requirements of higher compressive strengths, you may add the cement alone to get these values, but uneconomical. Can we supplement any other secondary material so that we can reduce the cement content? Yes, that is only the admixtures. Okay. So initially some 3 to 4% lime if we add to the black cotton soil, most of its plasticity properties can be overcome, and later if you go for the cement stabilization, then you can reduce the cement content. That is the purpose here. If organic content is present, 2% calcium chloride can modify the soil property, and poorly graded sand is to be modified by using or amended by the cement stabilization instead of using only cement. you can supplement fly ash so that it will be economical. That is what the admixtures means along with the cement stabilization. Benefits are similar to the lime stabilization only. These are all not very different from the lime stabilization. And some small study we have made here. That small study, what we have done is, you see, here in Telangana, all the Moram soils are not same. And to represent the widely ranging properties of Moram soils, we collected 3 Moram soils from different quarries, having the different plasticity and finer fraction. And for all of them, we have used on one side some 6% cement stabilization, and on the other side, naturally, in whatever the form they available, we used just what we can helplessly do in our field. So grade 2 metal is used to construct these stretches. All this is only gradation. Then these small stretches were constructed. As I told you, one side 6% cement is added to all the different types of morams, other side no stabilization. Like this, now ready, cemented and not non-cemented. You see, after the setting time, we also measured the Young's modulus and instant CBR. This is a loadman test to give the Young's modulus, and also clog impact. This gives the instant CBR value. Then also rain simulation we carried out using a shower. The shower we have used just to simulate the rainfall. Within 10 minutes, see how the aggregate is raveled, all the material is washed out. This is what is a reality in the field. If at all unscientifically, without any blacktop, if we believe only earth roads will stand, this is how every monsoon our roads will be damaged. This 6% cement stabilized systems, they are intact, no loss. And based on that, we further extended our study to understand further, can we really go for morams like concrete roads, cement stabilized moram roads as concrete roads in that direction? Because most of the Telangana morams by themselves are good, I have already told. The 80% is sand and gravel only, but that 20% if we can amend, it is looking like concrete only. So why don't we extend the study to that? So for that, one moram soil having this percent fines like this and subgrade, and ultimately we have got these properties for this part of the study, and these stretches were constructed like this. Here what we have done is, without stabilization, with 6% stabilization cement and again 12% cement, because my idea is, can we go for moram stabilized rural roads, something like that, like concrete pavements. For generally 10 to 12% cement is a minimum requirement, otherwise that much strength we do not get and durability. That is why we fixed 12% cement. And later conducted the cyclic plate load test on these stretches, and also clog impact and loadman test. As we have these gadgets, we captured the Young's modulus and the instant CBR. The cyclic plate load test, the data presented like this. See how we have done? Only one pressure repeatedly increased until here a loop is formed, no more settlement. Okay, until we reach this no more settlement loop, the testing is continued for every increase in the pressure. Ultimately, from this load settlement patterns, we captured the elastic deformation and also the total deformation. From this, the total deformation versus pressure plots were drawn. Interesting, you see, when cement stabilized, the deformations are very insignificant within one, just like that for these pressures. Then elastic deformation is very important to understand the pavement life. That also significantly reduced when cement stabilized. So this indicates high or increased life of the pavement. And another very important point, bearing capacity people normally use predominantly in engineering practice, but that understanding we have to be very clear. You see, without stabilization or with stabilization, the bearing capacity is not changed very much, right? Interesting. Settlements are changed. This is important. That means in the case of pavement engineering, whatever that aggregate soil, everything when they are little dry, bearing capacity wise, everything will be satisfied. But the settlement only a problem, right? So again, most of the pavements will be subjected to distress when the settlements cross the limiting value. Settlements allowed in the case of roads are very small. In foundation engineering, we allow up to 50 mm, but here it is only 1-2 mm only. More settlements means distress will be there in the pavement. That is why road should enjoy the traffic, not suffer under the traffic. This is the philosophy. Then modulus velocity without stabilization only 40 MPa, and when cement stabilized significantly increased. This also indicates yes, the material has become very stiff. It is not simply bearing capacity, stiffness matters in the road construction. That is what happened here. Even CBR significantly increased. Yeah, this is how even after severe monsoon rains, the 12% cement stabilized stretches are seen like this. See how pakka it is, like concrete road. So this is what we can promote also in future instead of crushing our own hills. Yeah, some initially I told some moram soils presented the liquid limit up to 62%. This we were interested. What is really making this moram to have this much plasticity? Where from it is getting? Out of interest, we carried out the mineralogical study. When XRD is carried out, this montmorillonite is having this this moram is having montmorillonite mineral. That is why only it is reflecting more plasticity. This we have understood. That means maybe there is anyway in Telangana, for example, where is moram? Top black cotton soil followed by moram. Immediately below the top black cotton soil, some layer of the morams may be contaminated in the long run because of the washing of these minerals from the black cotton soil down to the moram soil. So different types of morams, just now I was referring, having different degrees of plasticity. We have selected some 3 moram type soils, moram 1, 2, 3. These moram soils were stabilized using different lime contents and also cement contents, and all the properties were determined, OMC MDD, CBR values, everything complete. We have taken it as a scientific study, how we can understand the behavior of Telangana morams over a wide range of these stabilizer contents. And here cement also we used like that for different types of moram soils, got the OMCMDD and soaked and unsoaked CBR values. Yeah, continued. Then just to have an idea, CBR values are not significantly increased by lime stabilization because our moram soils are not that reactive within that 4-day curing period. That is why CBR was not increased. But with cement, there is a significant increase in the CBR value. Anywhere you can see with any type of moram soil. Just now I was referring, the one type of moram soil is having liquid limit 35%, fines 14%. Here liquid limit of the moram soil 43%, fines 20%. Here 62% liquid limit and fines 25%. So I told you these are some of the widely available natural moram soils we studied. But these moram soils are not responding to lime within that short period of 4 days soaking. And ultimately, all that data we use to get this type of chart, design chart. This helps a field engineer like this. For example, your target value of CBR for a particular pavement, say 30, and your soils may be having percent fines 25 to 30 and liquid limit is between 40 to 65. That means it is in the band 2. Yes, band 2. And requirement is 30, come down, okay, then drop down around 3% cement you can try. That means 2, 3, 4. These cement contents you can try with that soil, get the CBR, fix the exact content. Instead of blindly using the cement content for our experimentation, we can get the closely related value so that we can reduce our physical labor in the laboratory. Okay, that is how this chart will be very useful to select the initial cement content for the stabilization. And of course, see, these are all some of the advancements in the technology. Stable road concept has been introduced by Germans. Here, one equipment, it only digs, it only pulverizes, it only mixes, it compacts, it finishes the whole work. Very interesting, is it not? Smart. But such equipment we have to import to this country in large numbers so that we will be very much benefited by this technology. One road in Porank in Vijayawada, it is constructed using that technology, stable road concept. Simply, this is only cement stabilization only, but they say some product is added additionally to the cement so that 50 years guarantee they are giving. This type of equipment somehow we have to get for our Indian conditions so that only we will be successful in our stabilization techniques. See, after stabilization, it is looking like concrete. This is only soil only, stabilized with cement. But our story in Guntur, for one of the road stretches under the directions of the ministry, we suggested cement stabilization. But however, the contractor took up this work and after 2 months, he told he is helpless to get it pulverized as per the code. What I told, 25 mm, 100%. Where is 25 mm? Where is this size? And all 80% should pass through 4.75. It is also not that easy. So ultimately, we could not do anything, and we have changed the technique. We asked him once again, you level it, go back to the original idea of CNS layer concept, local available morum soil. We suggested them to place by 2 feet and over that again complete the road. That is how we have suggested helplessly, because we could not complete the cement stabilization here for want of equipment. Not that cement does not work, but equipment must be there. Otherwise, locally used, this tractor trolley, that harrows, all that does not work to the expected level as per the code. And on our campus, we studied a little to understand the black cotton soil, because most of the engineers pose problems with the black cotton soils. So we also are interested to understand a little so that first hand we will have some knowledge. Why to depend only on the books? This small study we carried out on NRIDA campus near the guest house. See what we have done. It is all black cotton soil. Whatever the code suggested, 2 feet morum soil first be placed. Over that, you can design your pavement and construct. Okay, good. That guideline we followed. Anyway, that is not permanent. Most of the roads again subjected to cracking and other problems, even when you follow that guideline. Then some people say sand. Okay, we use sand and again morum 30 centimeter, 30 centimeter, and in between geotextile also people say it is effective. Okay, use it, because after all, while experimenting, whatever the ideas, you can experiment after all. Experimented like this, friends. It's lime stabilization. Okay, we have excavated up to 0.6 meters, mixed with the designed lime content, compacted back. Again, morum is placed, compacted, everything is completed. Like that calcium chloride stabilization, okay, use it. Whatever the ideas like this, we have used and constructed small stretches to study. Now let us see how they have behaved. You see, this is the fate of these stretches. 30 centimeter sand and 30 centimeter thick moram cushion. Then you see how it is severely broken. You may ask a question, sir, when you are following the codal standard, still if you feel, what is that we can do? You please understand, most of our codal specifications in black cotton soils are against the swelling. But shrinkage is a severe threat. During the drying or desiccation under sun, the soil subgrade will be subjected to tensile stresses in the order of 100 to 150 ton per meter square. It's not small. What is this poor soil? Its tensile strength insignificant. That is why only they will break in case that desiccation happens in the subgrade. Here 10% lime we have mixed with the native soil, recompacted, and then 60 centimeter thick moram soil cushion is placed. Even then the system is cracked. Here cement again we have used to stabilize the subgrade, and 60 centimeter thick moram again placed. Even then also it is subjected to cracking. And anyway 30 centimeter thick sand and 30 centimeters thick moram and geotextile, even when we have used, the system is cracked. You may ask a question, even when geotextile is there, why at all it has to crack? Please understand, when sand is placed below, water could quickly enter into the system. Black cotton soil can be silenced when you can succeed to allow water entry slowly. If anything enters quickly, your techniques will fail. That is why only slow and steady. That concept is true even with the black cotton soils. Somehow we have to manage our drainage systems so that water ultimately enters, but let it enter slowly, by which there is a mechanism actually, cohesive bonds will be developed within the clay to self-stabilize the system, so that it will come to self-stability with little volume change. That is only our success. And ultimately here, even when 1% calcium chloride stabilized and then moram cushion is used, that is also cracked. That means whatever is calcium chloride, lime, cement, etc. may be good for the swelling control, but against shrinkage, they are helpless. See here the magic. Geotextile I have used directly on the prepared subgrade. Grass is removed, then a geotextile is placed, then 60 centimeter thick moram cushion is placed. No cracking is reflected to the surface. And I don't think that no cracks are formed in the subgrade, but because of the high tensile strength of the geotextile, that crack is not able to reflect to the surface. Okay, so that is how geotextiles can be definitely provided within these systems to control that reflection cracking to the top. Okay, thank you for your patient listening. For any queries, you are welcome.